This video is all about finding the GCF and LCM of monomials. Now, understood in the whole premise of this video is the fact that you understand how to find the GCF and LCM of numbers based on their prime factorizations. We'll do a quick review of that process as a part of the video, but if you have any questions on how to use prime factorizations to find GCF and LCM, you should go back and watch one of the videos related to those, because that is the process that we're going to use when it comes to taking monomials and finding their greatest common factors and least common multiples. So first, before anything else, we need to talk about what a monomial is. And a monomial is really just the mathematical term for a simplified expression that has only one term. So go ahead, pause the video, write down this definition. We'll give a few examples of monomials, and then we will move on to GCF and LCM. So the key part of making it a monomial, mono, the root for one, is the fact that it has only one term. That means as a part of the expression, we really don't see addition or subtraction anywhere. We see things like x cubed times y squared. That is a monomial, one term. We have the number 16, which is also a monomial because it has only one term. We can combine numbers and variables and have things like 14x to the 4th, y to the 7th. That is a monomial. Things like that. Those are the types of expressions that we're going to find the GCF and the LCM for. So let's start out with the GCF. Remember that when it comes to integers, we talk about the primes that are common or shared when we find the greatest common factor. So in the prime factorization of 12, which is 2 squared times 3, and the prime factorization of 16, which is 2 to the 4th, we just look for all of the primes that are the same in both numbers. Now, both numbers have 2's as a part of their prime factorization. And you can't share what you don't have, so we take the smallest number of 2's, and the GCF of 12 and 16 is 2 to the 2nd, or 4. And it turns out that process is pretty much identically the same when we have monomials. If we had 12x cubed and 16x squared, well, we would know, because we just saw it, that the GCF of 12 and 16 is 4. And that's not going to change just because we have some variables attached to it. What's different, though, is the fact that now we have some x's that could possibly be in common between 12x cubed and 16x squared. So if you look at these two expressions and seeing and thinking of the x's like primes, then the number of x's that would be common between the two of them, remembering that you can't share what you don't have, is 2. There are 2 x's in 16x squared. There are 3 in 12x cubed, but because 2 is the smaller number of x's, that is the greatest number that the two monomials can have in common. And so our GCF really is just the greatest common factor of the numbers, as well as all of the primes that are common between the two of them. And so that process is exactly the same as it was with regular integers. We've just added variables to it. And because we don't know what variables are, we don't know if the number that a variable represents is going to be prime, decimal, fraction. It could be composite, could be something that can't be written as a fraction, what we call an irrational number. Doesn't matter. We can't break a variable down any smaller than what it is. X just has to remain X. And in that sense, variables are very much like the primes of the algebra world. And we can think about them and treat them the exact same way when we're finding greatest common factors. So, for example, if we have 25x squared y squared and 35xy to the 4th, we can treat the x's and y's like primes, find the greatest common factor of the numbers, then the greatest common factor of the variable pieces, one variable at a time, and when we put all of those together, we're going to find the GCF of our two monomials. Now, you can go ahead and pause the video now to work on this on your own if you think you understand it. If you want to just let the video run and see how this process works before moving on to LCM, there are some practice problems at the end, then you can do that as well. But if you are going to pause the video and work on it on your own, go ahead and do that now. Otherwise, just sit tight for a second here, and then we will see how this process shakes out. So 25 as a prime factorization we know is 5 squared. 35 we know is 5 times 7. So now let's take this one at a time. Numbers, x's, and then y's. The only common primes are 5's between 25 and 35. And since there's only one of them in 35, that is the only 5 that we can have in common. You can't share 2 if you don't have 2. Now when it comes to x's, both expressions have x's, but 35xy to the fourth has only one of them. Again, you can't share two x's if you only have one. So a single x is a part of the greatest common factor, and then two y's from 25x squared to y squared. So the GCF of these two expressions is 5xy squared. So that's the greatest common factor of monomials. As you might have imagined by this point in the video, the process for finding the least common multiple of monomials is very similar to finding the least common multiple of integers. Again, 12 and 16 as integers, knowing that our process is one of two things. Either we can look at each prime that the numbers have, that is 2 and 3, knowing that our least common multiple is going to have to contain the prime factorizations of both 12 and 16 so that we can make either one of them, 12 and 16, both have to be factors. And we look at it and say, well, what's the greatest number of primes? In order to create 16, we need 4 2's, as it were. And in order to create 12, we only need 2. So 4 2's is what we're going to take. 4 is more than enough for 12, but does not have any extra for 16. Similarly, we need 1 3. And so our least common multiple of these two integers is 48, which is 12 to the fourth times 3. We can also approach it, as we saw in the other videos, of looking at this and saying, okay, let's take the prime factorization of 12, which is 2 squared times 3, and think to ourselves, how is it that we can use the primes that we have and make this look more like the prime factorization of 16? Well, in order to make 16 be a part of this, we need to increase the number of 2's to 4. And by doing that, we've created our LCM. 3's are good, 2's are good. Now we have the LCM of integers. Well, the exact same process can be applied using the idea that we talked about before, that variables are really just the primes of the algebra world, to 12x cubed and 16x squared. We know that the least common multiple from the last slide of 12 and 16 is 48. And now we can look at the x's that we have and say, if we want enough x's for 12x cubed or 16x squared, how many do we need without having any extra? Well, 2 is good enough for 16x squared, but we need that extra third one for 12x cubed because it's the greatest number of x's that we see. And so the LCM really is just 48x cubed. And so instead of taking the greatest number of primes in each integer, we take the greatest number of primes or variables between the two expressions and we create the LCM. We can also do it the way we did before, where we take one prime factorization and we try to make it look like another one. So if you'd like to pause the video, feel like you've got this and work on this on your own, you can go ahead and do that now. Otherwise, you can just sit tight for a second here, see the example, then we'll move on to some practice problems for you at the end. All right, so like finding the GCF of these same two expressions, we're going to take this one part at a time. We're going to take the numerical part, we're going to take the x's, and then we're going to take the y's. And then we'll also see it in the way that we did before, where we make one prime factorization look like the other. So 25, again, is 5 squared. 35 is 5 times 7. So if we're going to take both the greatest number of each prime, our prime factorization is going to need some 5's and some 7's. 1 7 is good enough for 35, but we're going to need 2 5's in order to create 25. 2 is more than enough for 35, but we need 2 for 25. So without any extra, we have 5 squared times 7, which is 175, but we'll get to that later, as the LCM of our integer parts. Looking at the x's, the greatest number of x's we see is 2 from 25x squared. So we'll need 2 of those x's to create either the prime factorization of 25x squared, or 2 is more than enough for 35xy to the fourth. And then for y's, the greatest number that we see is 4. So 175x squared y to the fourth is the prime factorization for the least common multiple of those two monomials. Now, if you want to look at it in terms of changing one prime factorization to look more like the other, let's start with 25, which is 5 squared x squared y squared, and we go prime by prime and see what we need to add. We've got the 5's for 35. We need a 7. So let's add the 7 there. We've got more than enough x's for 35 xy to the fourth, but in order to make sure that y to the fourth is a part of that prime factorization, we actually need to increase the number of y's by 4, and we end up at that same factorization that we did before. All right, so now it's your turn to do some practice problems. Go ahead, pause the video, find the GCF and LCM of these two sets of monomials. Come back when you're ready to see the answers. There's one more slide after this, but GCF and LCM of both of these sets, and then come back to see that process. So the prime factorization for 9x to the fourth is 3 squared x to the fourth. For 12 is 2 squared times 3x squared. I'm not going to spend a whole lot of time on the numbers because we've seen that before, and if you need a little bit more review on that, you can go back to the other lessons. The GCF of the numerical part is 3. The LCM of the numerical part is 2 squared times 3 squared. Which is 36. As far as the x's are concerned, the least number we see, which is the amount that they can share, is 2, and the greatest number that we see, which is what we need for the LCM, is 4. So GCF is 3x squared, LCM is 2 squared times 3 squared times x to the fourth. For 15x squared y squared and 25x cubed, 15 is 3 times 5, 25 is 5 squared. Again, I'm not going to spend a lot of time on the numerical part. We're just going to say what it is that they are, and then we'll move on to the variables. So the only thing that they share is a 5, so that's the part of the GCF from the integers. The LCM is going to be 3 times 5 squared, which is 75. Now looking at the variables, they both share some x's. The things they have in common are 2 x's, and we'll need 3 x's in order to make the LCM, because that's the greatest number we see. And now they don't share any y's, so there are no y's as a part of the GCF, but there are 2 y's for 15x squared y squared, so we're going to need to have 2 y's as a part of that prime factorization for the least common multiple. One more set of expressions for you to find the GCF and the LCM of. Go ahead, pause the video, work these through. You'll notice the left-hand ones only have variables, so it should be relatively quick, and then come back when you're ready to see the answers and wrap up with the video. So for both the GCF and the LCM of our expressions on the left-hand side here, x squared y cubed z to the fourth and x cubed y cubed z squared, we're going to have 3 different variable types here. We're going to have x's, we're going to have y's, and we're going to have z's. So for the GCF, we have x's, y's, and z's. We're going to need 2 x's because that's the number that the 2 can share. X cubed, y cubed, z squared has 3 x's, but x squared, y cubed, z to the fourth can't share 3 x's because it doesn't have 3, so we take the smallest number. They both have 3 y's, so that's what's in common, and there are 2 z's on the right-hand side. They're in the right-hand expression, so our GCF is x squared, y cubed, z squared. Now let's take a look at turning one expression to another. So we start with x squared, y cubed, z to the fourth, and we go variable by variable and see what we would need to add to make it look more like the expression on the right. And so we need to add another x in order for x cubed to be a part of the prime factorization. Y cubed is perfectly fine because they both have a y cubed, and z to the fourth is perfectly fine. That's more than enough for the right-hand expression, but exactly what we need for the left. And finally, on the right-hand side here, not going to spend a whole lot of time on this one because this video is already getting fairly long. We've got 15, which is 3 times 5, 45, which is 3 squared times 5. So the GCF of the numbers is 3 times 5. The LCM of the numbers is 3 squared times 5. And now for the x's and y's, they can share 3 x's because there are 3 x's, and they can share 1 y because that's all that 15x cubed y has. And then for the least common multiple, we need 4 x's because that's what we see in the right expression, and we need 3 y's. So it turns out 15x cubed y is actually a factor in the algebra world of 45x to the fourth y cubed. So that is the process of finding the GCF and LCM of monomials. Just treat the variables that you see like primes and use the exact same processes that you did to find the GCF